Good afternoon, Panthers. It's Dr. Augustine, and today we are going to be talking about how the geometry impacts the polarity of a molecule. This is actually section 10.5 intro. So we just talked about Lewis structures, talked about taking a Lewis structure and figuring out what the geometry is going to be, and then using that geometry to then figure out whether a molecule is polar or nonpolar. Now, you might be thinking to yourself, well, didn't we already talk about polarity? Back in chapter 9, this figure was shown, and it shows that if you have a difference in electronegativity of two different atoms between 0 and 0.4, we call that a purely covalent bond. If it's from 0.4 to 2.0, we call it a polar covalent bond. More than 2.0, 2.0 to 3.3, we call it an ionic bond. Okay, so that was what we talked about back in chapter 9, and the example molecules that we gave for that were like HH or carbon, hydrogen. I'm going to draw with the geometries now that we know how to do that. Or CO2. Nope, I didn't use CO2. We'll hold off on that one. HF was another one we used an example of. All right, and remember we said you measure the difference between the electronegativities, so you want delta electronegativity between the two atoms. So obviously in the case of carbon, in the case of hydrogen, we've got one hydrogen, we look it up and we say, it's 2.1, so 2.1 minus 2.1, that one is going to be 0. So delta En is equal to 0. So along our scale, we would say 0, that's a purely covalent bond. Carbon-hydrogen would be 2.5 minus 2.1, and that's equal to 0.4. Go on our scale, 0.4. In fact, that's why they choose 0.4. We would say that one is also purely covalent. HF, on the other hand, is 4.0 minus 2.5, so that's going to equal to 1.5. It's going to put us somewhere up in this range right here, and we would say that is a polar covalent bond. Okay, there's a review from chapter 9. And remember we did something like this. We said if you have an HF molecule, you've got extra electrons over here, and when we were sketching out the electron distribution, it might look something like this. All right, and we would say that there's a partial negative charge on the fluorine, we'd say there's a partial positive charge on the hydrogen. Another notation we used was we use an arrow pointing towards the more electronegative element, or where the negative sign is. And so we have a couple different ways to represent this. We can use the electron density. We don't usually do that. It's hard to draw. You can use these partial positives or partial negatives, and we can use this arrow notation to indicate which way the dipole moment is pointing, and we would call this a polar molecule. So you might be asking yourself, well, why are we talking about this again? We already talked about this. Before we answer that question, let's just take a look at the effect then. If we have an electric field of some sort, and we have these random molecules, like let's say these are HF molecules in between these plates. We have no electric field. They're just going to randomly be distributed, all pointing in different directions. But if we put an electric field on, so we have a negative on this side and a positive on this side, the molecules tend to align with the negative side pointing towards the positive plate and the positive side pointing towards the negative plate. Okay? That's called having a dipole, a permanent dipole. Okay? Polar molecule with a permanent dipole. So a good question to ask yourself is, why are we talking about this right now? We already talked about this. So now that we know the geometries, now we can take a look at some molecules that, unlike these with just two atoms, have a couple of different atoms, and they have a shape associated with them. So if we want to figure out the polarity of a molecule, we need two different things, two criteria that we need. One is we need to know the geometry, and the second thing we need to know is whether the bonds are polar or not. So this is like a chapter 9 idea, and now this is a chapter 10 idea. So let's take water as our example. Water We know that the hydrogen is a lower electronegativity than the oxygen, so we're going to end up having the arrow from that bond pointing in towards the hydrogen. We have an arrow from that bond pointing in towards the hydrogen. And the net result is that the overall dipole is pointing through the middle of the molecule. We have a positive side to the molecule on the hydrogen side and a negative side to the molecule on the oxygen side. Now, we're not going to get into the math on this, but if you really want to figure out exactly what that green arrow should be, you take the angle and the direction, in other words, the difference in electronegativity between one of the hydrogen oxygens, you do another one between the other hydrogen and oxygen, and the resultant between those would be the net dipole moment. Okay, this is called vector addition. You have an angle plus a magnitude, and you end up with this vector. That's the green vector. I'm not going to have you worry about how calculating the actual magnitude. I just want you to recognize that the two red arrows add together to form this green arrow. All right, so there's an example with water. Let's take something like ammonia. That's another example we've done before. This is a nitrogen, hydrogen, hydrogen, hydrogen with a lone pair. Each nitrogen-hydrogen bond is polar, a little bit polar. And if we add those three things up together, you end up with a permanent dipole pointing up through the middle of it. So we have a negative side on the hydrogen side again, or excuse me, a positive side, and a negative side on the lone pair side. All right, let's take a look at a molecule like carbon dioxide. We look at the individual dipoles. There's going to be a dipole pointing towards that oxygen. There's going to be another dipole pointing towards this oxygen, because oxygen's more electronegative than carbon. But what do you notice is going to happen between these guys? They're going to end up canceling each other out. So mu is the symbol that we use for the dipole moment. Mu is actually equal to 0 on this molecule. So this is a non-polar molecule. This one's polar. This one's polar. This one's polar. All right? So if there's a net dipole, we call it a polar molecule. If there's no net dipole, we call it a nonpolar molecule. We'll give you one more example. All right, here's one of our friends. We've done this one a few times. These bonds are not really polar. These are basically nonpolar bonds. Slightly polar, but they're 0.4, so basically nonpolar bonds. So this molecule would be nonpolar also. All right, let's take a similar molecule. We're just going to make a slight modification to this. And let's put a fluorine on the end. Okay? Now, stop and think about this one for a second. Carbon fluorine, big difference in electronegativity. So there's a large bond polarity. And this is where you got to be careful. You can't just look at the electronegativity. So the first criteria is electronegativity. This one definitely has a polar bond. It's a strong polar bond. Fluorine is the most electronegative element on the periodic table. But what do we notice is happening with these 4 different bonds that are all pointing 109 degrees away from each other? They're all going to cancel each other out. So again, the dipole moment is equal to 0 on this. This is also a nonpolar molecule. So don't be tricked with the fluorine atoms on there into thinking that it's polar when in fact it isn't. All right, now if we make just a slight modification to this, now this is essentially a molecule in between those 2 other ones we just looked at. What do we notice is going on here? Well, we got a bond polarity here. Teeny tiny ones here. These are basically nonpolar. So this molecule is a polar molecule with the dipole pointing up towards the fluorine. Okay, so what have we learned here? we have learned that we need two criteria. We need to look at the electronegativities, the differences, just like we did before, but we also need to take a look at the geometry of the molecule once it's assembled. And if they're symmetric and they cancel each other out, it's going to be nonpolar. If they're not symmetric and they don't cancel each other out, it's going to be polar. All right, now let's take a look at one final question then, kind of related to this. We can use polarity of the molecule to tell us something about it. So if we have two molecules that are polar, let's take two water molecules. They tend to arrange themselves. Remember, this is the positive side of the molecule. This is the negative side of the molecule. If another water molecule comes around, it's going to tend to arrange itself with the negative side pointing towards the positive side. In other words, this is the sort of interaction that these guys have with each other, is positive to negative. So there are attractive forces between these molecules that sort of hold them together in this orientation. So we can use that to our advantage because things like the melting point and the boiling point are profoundly impacted by whether something is polar or not. The boiling point and melting point go way up if you have polar molecules compared to nonpolar molecules. So let's take a look at an example of a molecule called dichloroethylene. It has two carbons. It's got two hydrogens, and it's got two chlorines. All right, so the formula is C2H2Cl2. All right, now if we look at the geometry of, let's say, we'll call this carbon 1 and carbon 2. If we look at the geometry of carbon 1, how many electron domains does this guy have? 1, 2, 3. So what should the bond angles be around that central carbon? They should be 120. Trigonal planar, and there's no lone pairs on that carbon, so they're all going to be 120, and same thing here, 120 degrees here, 120 here, 120 here. Trigonal planar, the whole thing is planar and symmetric with one another. All right, now, if you look at this molecule, though, you'll notice there's different ways you can arrange this. And by the way, that double bond is called a non-rotatable bond. The double bond locks it into position. So I can write this molecule a couple of different ways, and they're actually different. The properties are different from it. So there's one way I can write this. Here's another way I can write this. Chlorine's opposite sides. That's the second way we can write it. And the third way we can write it is with the chlorines on opposite sides of the carbon, but on the same carbon. Okay, we call this arrangement when they're on the same side of the atom, we call that a cis arrangement. And if they're on opposite side, we call it a trans arrangement. All right, so there's two different types of trans molecules and one type of cis molecule. So suppose we have, and by the way, these are called isomers, structural isomers. It's the same atom that's been rearranged differently depending on how the atoms are attached. This is not a resonant structure. We haven't moved the electrons around, we've actually moved the atoms around. So an isomer means we move the atoms. A resonant structure means we just move the electrons. All right, so how can we tell these guys apart from one another? Is there a way we can tell them? I'm going to erase this. Okay, that didn't work. How can we tell these guys apart from each other? Well, we're talking about polarity here, so let's take a look at this. This one, that carbon-chlorine bond is polar. Carbon-chlorine bond's polar on this one. Carbon-chlorine bond is polar on this one. So let's call this structure A, let's call this structure B, and let's call this structure C. what would be true of A and C, but not B? So A and C, A is going to have a dipole moment that goes between the two carbon atoms, between the two chlorines. C is going to have a dipole moment that points between the two chlorines on one carbon, and B is actually nonpolar. So the melting point and the boiling point are going to be less on molecule B. So if it's molecule B, we're going to see a big difference in the melting point and boiling point. If it's A or C, we're going to need to do a second experiment, a different experiment, to figure out which of these two it is. We're actually going to have to do some spectroscopy or something. All right, but the point I want to make here is you can actually use the polarity of the molecule to figure out differences in structural isomers. Even though it's the exact same arrangement of atoms, they're going to have very different properties from one another. Okay, that's going to wrap up section 10.5.